Hello everyone, today we'll talk about the solution to the problem count number of maximum bitwise-OR subsets. Of course, knowing what bitwise-OR is a prerequisite to solve this problem. We know that if we have a set of numbers, then the bitwise-OR of that set is a number that at every bit position has a 1 if at least one of the numbers has a 1 at that position. In other words, it has a 0 exactly when none of the numbers have a 1, all the numbers have a 0. And that leads to a very important property of OR, which is mirrored in AND, because if we have an OR of this set of numbers, and we add another number to that set, then OR can only increase or stay the same. That's because for every position that we have a 1 in our bitwise OR of the whole set, there is at least one number in the set that has a 1 at that position, so nothing happens to that number, it still exists. And V, even if V is smaller than this OR, maybe it has a 1 on a new position which will increase our bitwise OR. So, the preliminary question of what is the maximum possible bitwise OR of a subset of nums? Well, this is just the bitwise OR of the whole nums. To calculate it, we can use the reduce operator to reduce the list of numbers to a single number. We start at 0 and we use the OR operator, which we can use as operator.OR. Here we have this required floor symbol. That's because OR is a keyword in Python. Okay, so this is the target. We want to count the number of different non-empty subsets whose OR is equal to target. And while we could think about some smart solutions, in this problem, it's enough to just write a simple backtracking algorithm. So we'll be maintaining the counter, running our function to calculate the backtracking, and return the counter. That function will, of course, recurse, and it will follow the standard practice for how you write backtracking algorithms. So if you have your preferred option for writing backtracking, then do it your way. And I, of course, have my own preferred way, which is very similar. Every backtracking function essentially looks the same. So, since we want to update this count, which is an integer, we have to write non-local count within the function. And now, how do we know if we have reached the bottom of the recursion? Well, we'll be modifying the nums list. So if that list is empty, that means that there is no more decision to make whether to take or not take a number. So we just update our count of subsets that have the bitwise OR be equal to target, which we can write something like this: count plus equals car equals target. It might look pretty weird because of those two symbols, but yeah, I think this, while it might look pretty weird, this is a pretty common way of writing things, so it's nice to be familiar with it. Because car equals target is a boolean, so it will be equal to 1 if car equals target, 0 if car doesn't equal target. And of course, in that case, we just return this is all that we have to do because we've reached the bottom of the recursion. Otherwise, we have to recurse, and here is where the backtracking portion appears, here is where the exponential portion appears. We know that we want to decide whether we take the next number of nums, and of course we have to remember to put it back after all the recursive calls. And if we take it, then, or maybe first if we don't take it, then our current OR stays the same. So we just recurse without that element, but with the same bitwise OR that we have had previously. And then we also recurse with adding the value v to our subset, so we have to calculate the bitwise OR of the current OR and the new number. So this is the standard pattern when it comes to backtracking. So remove the element from the pool, remember to add it back into the pool, and then recurse while adding this element, well, in this case, not adding this element to the set, and then adding this element to the set.